Good afternoon, everyone. My name is Branka Tamaris. I'm the Events Coordinator at the Melbourne Energy Institute. Before we begin, I'd like to acknowledge that today we are gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people who have been custodians of this land for thousands of years, and we acknowledge and pay our respects to their elders past and present. Moderating our lecture today is Professor Pierluigi Mancarella, Chair Professor of Electrical Power Systems at the University of Melbourne. Our guest speaker today is Chiara Lo Prete, Associate Professor of Energy Economics in the John and Willie Leone Family, Department of Energy and Minerals Engineering at Penn State University. Her research centres on the modelling of energy markets and systems with a focus on the area of competition and design of electricity markets, energy system interdependencies and energy geopolitics. Recent work has used tools from economic, mathematics and engineering to study natural gas markets designed to enhance grid reliability during winter emergencies and electricity market structures for wind energy integration and resource adequacy, the weaponisation of electrical trade and emission leakage in the Western US. Before joining Penn State, Chiara was a ZIF Environmental Fellow at Harvard University from 2012 to 2014. She earned a BA in Economics from Lewis University, an MA in Energy Economics from the Scuola Mattei, and a MS and PhD in Environmental Engineering from the Johns Hopkins University. Please welcome Chiara.
Thank you. Thank you very much for the introduction. Can you all hear me okay? Both here and on Zoom. I hope everything looks good. Okay, so thank you for having me. I'll try to stay here, not to move too much. Thank you for having me today, and I'm excited to be in Melbourne for the first time. So thank you, Franca. Thank you, Pierluigi, for having me here. So today, like Franca mentioned, I am an energy economist. My background, my bachelor's was in economics, but then during my PhD, I did a lot of modeling and systems modeling in particular. And over the past few years, I started thinking a little more about interdependencies between gas markets and electricity systems. A lot of people have focused their attention on modeling the two systems together, gas systems and electricity systems. And a lot of people work on electricity market design, and some of the work that I do is on electricity market design. But very few people think about how imperfections and frictions in the gas market affect what happens in the gas systems. And so I figured that would be a really interesting topic for me to explore. And that was part of the reason why a couple of years ago, we applied for a grant from the National Science Foundation to study an issue that has been creating a lot of trouble in the United States, in some parts of the United States. And the issue, the motivation in short is presented here on this one slide. The United States has become, like many other parts of the world, very reliant on natural gas for electric power generation. And in 2023, about 40% of the total generation capacity was fueled by natural gas. And this growing dependence has exposed some vulnerabilities during critical periods. And specifically, we're looking here in this research at winter emergencies that are caused by cold weather events, by winter storms. These are instances in which there is a coincidental peak demand for natural gas And this demand comes from the traditional users, which are the local distribution companies or LDCs. I'll keep referring to them as LDCs. Those are the local gas utilities that have traditionally used natural gas for space heating to serve residential and commercial customers. But now the new end users on the market is the electric power sector, the power plants. And so what happens during these winter storms is that there is this coincidental peak in gas demand from the electric power plants and the LDCs, the local gas utilities. And this poses threats to electric grid reliability for reasons that I'll explain in a moment. And the issue has become very problematic in some parts of the United States. I live in Pennsylvania, and that is one part that has been affected here, like the rest of the Northeast. And that's because in the Northeastern United States, building new pipelines is not, let me put it this way, it's not very likely in the short term for a number of reasons that relate to local opposition, political reasons, environmental opposition. But due to a number of reasons, expanding the pipeline capacity is not very likely. And so what we're trying to do here is to think about ways to allocate gas in a more efficient way during these very critical periods. So under the constraint of the existing pipeline capacity that, like I said, is unlikely to change in the near term, can we think of ways in which we can reallocate the existing gas during these critical periods? And that is pretty much the objective of the project that was funded 2 years ago by the National Science Foundation. I do want to say that we're not taking any policy positions, or we're not making any recommendations on the fact that there's no need to expand capacity. That's a separate story. Sometimes I get questions on that, but that's not kind of part of what we're studying. Our assumptions, one of our assumptions, if you want, is that the pipeline capacity cannot be expanded in the near term. So here's going to be with that motivation, here's going to be the outline of my talk. I will give you a little bit of background on what's happening on the gas market and what types of contracts the power plants can sign, and again, what frictions there are right now that prevent them to get access to gas. Then I'll talk about a proposed initiative that we modeled to see if, again, this proposed initiative could help enhance grid operations during a cold snap, during one of these emergencies. I'll give you an overview of the models. I did share a paper with Franca and did I send it to Pierluigi or Franca? I don't remember. Maybe to Pierluigi, but I don't know if the paper was shared. But if you'd like to share it, I'd welcome any feedback that you may have, because this is still work in progress. We haven't published it yet, so any feedback is welcome. But I won't go into the details of the model formulation. I will just give you a very kind of high-level description of what the model is doing, and happy to talk about the details later. I'll show you a couple of findings, and then I'll conclude and I'll tell you what we're trying to do next, and hopefully get your feedback and hear your thoughts on how I've been talking to a number of people over the past few days here in Australia, and learning about what you are doing to kind of manage and allocate gas on your existing pipeline capacity. So I'd welcome additional discussion and feedback on that front. Okay, so let's start with some background. I already told you that natural gas supply interruptions represent a significant problem. And in terms of contribution to power outages. I am showing you here some statistics that this is published material from some of the reports that were written by the grid operators or the Federal Energy Regulatory Authority, which are the FERC. So here on your, let's see, on your left, you can see some stats from the polar vortex of 2014 from PJM. And you can see that in 2014, about 23% of total outages in PJM were caused by natural gas supply shortages. 4 years later, in 2018, there was another major storm, which has the name of bomb cyclone. And even there, about 25% of the outages was caused by natural gas supply outages. That is interesting because between 2014 and 2018, PJM actually implemented something called capacity performance. And so in principle, that number should have gone down, but in fact, it didn't go down very much. And so there are still some big issues related to procuring gas at power plants. Here on my left and your right, you can see some statistics from the most recent winter storm, that major winter storm that the region had, and that is Winter Storm Elliott in December of 2022. Even during Elliott, gas supply issues represented about 30% of the cost of power outages. So these are, again, just a couple of events. If you look at different regions like Texas in 2021, you will get similar orders of magnitudes. So that's more or less the contribution of natural gas supply outages to power outages. And of course, this number is kind of encompassing a number of things, right? Because a gas supply problem can be due to a failure at the pipeline. For example, the compressor may freeze, there might be a compressor outage, or there could be issues at the wellhead. There could be wellhead freezes, which were a significant problem, for example, under Winter Storm Uri. So this number by itself is not telling you exactly what the issue is. It's just telling you that there is a problem with natural gas supply. So then let's unpack that a little more. Why can't gas generator why can they get gas? So that's where when we started looking a little more into the contracts. So in the US, and I think in Australia it's the same, gas-fired generators can arrange for gas sales and delivery using two types of contracts that go under the name of firm and interruptible. Firm contracts usually establish a higher order of priority for the fuel requested, and they guarantee gas delivery under most circumstances. I want to emphasize the word most, because what in fact happens is that during some of these winter storms, the pipelines start calling OFOs, which are critical periods, and they don't even satisfy the contracts, the firm contracts. So those are the firm contracts. The interruptible contracts are contracts that obviously cost less, lower cost service with reduced delivery priority and very high chance of being curtailed during periods of high demand. Now, in 2023, about 80% of the gas-fired generators in the United States procured their gas with firm contracts, and the rest, about 20%, was procuring gas through interruptible contracts. But here's the catch. The number that I'm showing you at the top actually masks a lot of regional variation. And I'm showing you here a figure that was created by the Energy Information Administration. This is for 2016, but numbers haven't change dramatically if you bring it up to 2023. So you can see that the Northeast, which is the region of interest for our study, the Northeast actually has a much higher share of interruptible contracts. Even there's a lot of variation between states in the Northeast, and I won't go into the details, but one of the reasons why gas generators in the Northeast are reluctant to sign firm contracts is because the electricity markets that they operate in do not provide sufficient incentives to compensate the generators for the very high fixed costs that would have to be incurred to pay for a firm contract. A firm contract would have a very high, again, sort of a fixed cost that would have to be paid regardless of whether it's a reservation, it's called a reservation charge. That has to be paid regardless of whether or not the customer is using the capacity. And then there's like a volumetric charge. And so the issue is that the electricity markets in the region do not provide sufficient incentives for to compensate generators for the higher cost associated with the firm contracts. So now the story becomes even more interesting when you learn that even gas generators with firm contracts can't get gas. This is counterintuitive, right? Because you would say, okay, wait a second. So these generators are paying for firm gas, but then they don't always get gas. Yes, that's exactly what happens. And I'm showing you here just an excerpt from a FERC report that was published after Winter Storm Elliott in 2022. And so you can read the statement, but pretty much what happened in Winter Storm Elliott is that there were more instances of curtailments to gas generators with firm contracts in terms of megawatts, like in terms of megawatts of capacity that was lost. More generators lost, like they were not able to operate their capacity because they lost access to firm gas than losing access than those who lost access to interruptible gas. And again, that's very counterintuitive, and even FERC says it, right? They say somewhat paradoxically, they realize that that's a problem right there. So obviously, that's when we started investigating what is happening as part of the NSF project. And unfortunately, we it's not, you can't really find a place that gives you, even these reports are pretty opaque when it comes to the real reason why gas-fired generators with firm contracts lose gas. But I'm just gonna give you a sense of what the information that we gathered by reading reports and talking to the stakeholders, including the pipeline folks, the pipeline reps, the gas generators, and other, again, key stakeholders in this market. So obviously, I already mentioned this. Equipment failures may be one of the problems. So if you have a compressor outage, obviously that can reduce the capacity of the pipeline and may not enable a certain customer to get gas. That is, however, not the focus of our research here. Another reason is due to the fact that sometimes pipelines operate pipeline, the pipeline operators, I should say, operate the pipeline below the maximum capacity because they're trying to manage something that is called line pack. Has anybody heard this term before? Line pack is to helps maintain pipeline reliability. It's like a buffer, if you wish, between supply and demand. And what happens during during these winter emergencies is that line pack levels are higher because you want to handle increased demand on the pipeline. So if you want to try and have higher line pack levels, then the pipeline operators have to operate the system at higher operating pressure, which reduces the steady state pipeline capacity. So the reason why this is important is because even if, say, contracts were signed at the steady state maximum capacity of the pipeline, once you start bringing in this like operational issue, then there is a reduction in the actual capacity that is operational. And so the pipeline operators, in some instances, that's what they claim, they must curtail to maintain security on the pipeline. If they must curtail, then they will give priority to the LDCs, to the local gas utilities. They will generally decide to curtail power plants instead of LDCs. And so that's one of the reasons why the power plants can't get access to gas. There are also no-notice contracts. These are special types of firm contracts. They're like legacy contracts that these LDCs have had for decades now, and they continue to have these contracts. And in situations of emergencies, the LDCs can kind of take higher priority over the power plants. So that's another issue. There are also distinctions between different types of firm service. And that's where it took us quite a while to unpack this issue in particular. The problem, so what I'm showing you here is a representation of the gas day. So there are some opportunities for the shippers to nominate their gas on the day before gas actually flows. And shippers have 5 opportunities in the United States to nominate their gas. There's going to be 2 gas cycle in T-1, which you can see there. They're called the timely cycle and the evening cycle. And then there's like 3 additional cycles in the day in which the gas flows. Now, we are plotting there even the scheduling of the electricity market to give you a sense of the problems and misalignments that there are between these 2 markets. One of the issues that gas generators have often kind of raised is that the very first nomination cycle, the timely cycle, happens shortly after the clearing of the day-ahead electricity market. So the timely cycle is where it's the most liquid gas cycle, and the day-ahead market is generally where most of the electricity gets scheduled ahead of the day in which power gets delivered. So as you can see, there's only half an hour between the 2 because the day-ahead results in the electricity market are published around 12:30 Central Time, but the timely nomination schedule is at 1 p.m. Central Time. So the gas generators only have about half an hour to make those decisions. Now, the issue, though, is not even that. This is creating frictions, but the issue is that because of these distinctions between secondary firm and primary firm, what seems to be happening is that in some cases, power plants have to, like the power plants that are called later in the day, say after the day-ahead market, maybe they're called very close to real time. They try to submit nominations for primary firm service, but they can't they can't schedule those nominations. The reason is that according to FERC policy, secondary firm that is scheduled in the earlier cycle cannot be bumped by primary firms scheduled in later cycles. So what seems to be happening is that the power plants have an issue because they try to submit primary firm nominations that in principle should be satisfied first, but there is already secondary firm that is scheduled during an emergency. And so they can't get gas. We're trying to understand, we're trying to quantify how prevalent this issue is in reality, but this seems to be an issue that has come up during some of these winter storms. So now, with all of that background in mind, here's the recommendation part and the policy part. So obviously, this is a big problem, and a number of forums and stakeholder groups have been thinking about what to do about these issues of gas-electric coordination. I don't know if any of you is familiar with, has anybody heard of NASB before? So NASB is a North American Energy Standards Board. It's a forum to let's see, an industry forum for the development and promotion of standards in the electric and gas industry. And so in 2023, they came up with a report that is publicly available, and they issued a number of recommendations to try and help better coordinate the two systems during emergencies. And in particular, their recommendation 6 talks about this idea of facilitating contractual agreements between end users. And the end users in question here are obviously, on the one hand, the power plants, on the other hand, industrial customers that may not need gas during a winter emergency to maintain their production process, and they may be able to perhaps switch off during that particular emergency. So that was the NASB recommendation in July of 2023. 6 months later, 4 grid operators, PJM, MISO, let's see, who else? ISO New England and SPP, they came up with a joint position paper. And again, the position paper was trying to do something very similar to the report of NASB in the sense that they were kind of proposing to the stakeholders a number of initiatives that they thought could be potentially interesting. They're just proposing the initiatives, but they're not quantifying or providing any analysis to support their suggestions. So these are just ideas, if you wish. And one of their ideas was to prioritize gas to the power plants during an emergency. And again, this was stated in perhaps just one paragraph, so it wasn't like explored at length, but the idea was the proposal was a proposal to FERC, and they were saying, okay, FERC should act and should make sure that during these emergencies, power plants can get prioritization, can get priority gas, pretty much, right? So FERC should explore this. So we kind of combined the two ideas that I just presented to you, and the proposed initiative that is explored in the paper that I shared with Pierluigi is considering the use of these advanced exchange agreements, in other words, these bilateral contracts between the end users. And we refer to these contracts with the term AEAs, so I'll keep referring to them as AEAs. The AEAs would be used to prioritize gas to power plants during an emergency. It seems, based on the NASB report, it seems that some AEAs already exist. So this is not like a totally new thing that has never been tried. They do exist, but they're not very common. And there are some barriers to their implementation on a larger scale. So, and we've been asking what those barriers are, but that's a separate question. In terms of what these contracts look like, there are a few things I want to emphasize. The first one is that these are bilateral contracts. They are not contracts that happen in a market. They would happen kind of bilaterally between the end users. We are thinking of, I mean, the way we presented these contracts in the paper is that these would be contracts between customers that hold firm contracts. In other words, both parties need to hold firm contracts. This may be overly restrictive, and maybe we can talk a little bit about that later, because assuming, if you think about it, assuming that the industrial customers get a compensation that is good for them, then even if you have power plant with an interruptible contract that is willing to pay, then perhaps there shouldn't be any issues with establishing a contract between an industrial customer and a power plant with an interruptible contract. The one key issue that I want to emphasize, though, is that the power plants that would enter these contracts are only a subset of power plants. It doesn't make sense, obviously, to have every power plant enter into these contracts, right? It would be too costly and not efficient at all. But the power plants that are at very critical locations on the grid, and specifically the power plants that support grid reliability needs, are the power plants that would need to enter these contracts, because those would be the power plants that need gas. And the last thing, which I already mentioned, is that the industrial customers would receive compensation for releasing their gas, obviously. And this compensation is at their value of lost load, which is the value of lost load for gas. It's not the value of lost load that you might be more familiar with, the one for the electricity customers. And one interesting thing that I didn't know, but when I saw some of these estimates of the gas vol, is that it seems that the gas vol is much lower than the electricity vol. The typical number that we'd have in mind in the US is something like $9,000 per megawatt hour. And the reason why I'm using this number is because this was the highest cap to the energy market in Texas that was supposed to reflect the value of lost load of electricity customers. It's now 5,000, so that has been changed. But relative to that $9,000 per megawatt hour, obviously on the same per unit energy basis, the gas vol is much, much lower than that. So now, the goal here is to try and quantify the impact of this proposed initiative. And by that, I mean that we want to see how much that initiative can contribute to enhancing reliability in an actual grid. And that is measured, obviously, the key thing we can measure is the reduction in unserved energy if we implement this particular type of contracts. And also another thing we can measure are the net benefits of the initiative. What do I mean by net benefits? Well, there's going to be, if we implement these contracts, on the one hand, there's going to be a reduction in the costs of operating the system. And that's primarily because there is a reduction in unserved energy. So there's going to be a reduction in the costs of unserved energy. On the other hand, however, there's going to be a higher cost because there's a compensation that has to be given from the power plants to the, from the power plants to the industrial customers. So there's going to be a reduction in cost, but a higher cost on the other side. And the difference between these two terms is the net benefit that I'm referring to here. Obviously, we'd want this net benefit to be positive for the initiative to make sense. And we also want to see how much, like, what is the magnitude of that net benefit? Is like 1% of the original costs? Is it 50% or whatever number it is? So that's what we're trying to accomplish here, we're trying to quantify the impacts of this initiative. So to answer the question of quantifying the impacts, we use optimization models. And specifically, again, like I said, I won't go into the details of the models, but these are models for the operations of a gas electric system, of a gas electric network. The goal, the objective of the model is to minimize the cost of serving electricity demand in the network. And this is subject to constraints that govern electricity flows, constraints that govern gas flows, and constraints that establish the order of priority in which gas customers would be curtailed during a winter emergency. That's kind of one of the main differences between the model that we developed and the previous models that were kind of oblivious, or they didn't consider contract types, and they didn't consider the order of priority in which these different gas customers would be curtailed during an emergency. The second point is something, again, that I want to emphasize. We're not considering instances of pipeline failures. We're not considering instances in which there are compressor outages. And we're also not considering problems on the supply side, on the production side. We are aware that those are real problems. They were problems that happened, that we're not trying to kind of discount them, but they're just not what we're trying to model here. The reason why the natural gas supply interruptions happen in our model is simply because there is not sufficient pipeline capacity. Like I said at the beginning, that is the main constraint in our model. And that is the reason why then the pipeline operator has to curtail. So what are these two models? In the baseline model, like I just said, the purpose is to, I just described it. So I just want to give you the order of priority that gets implemented in the baseline. The baseline is supposed to mimic, obviously in a modeling setting, so in a simplified setting, but it's supposed to mimic what is happening today in terms of prioritization. If the pipeline operator has to curtail, priority is given to the residential and commercial customers. So the local gas utilities that serve those customers are never curtailed in our model. They always get 100% of their gas. The next ones that have priority are the customers with firm contracts for the reasons that I explained. And so you can see that the two, I don't know if I have a clicker or if there's any way in which I can point to, well, I guess you can see them though, that the two boxes that are in kind of a rectangular shape, those are the ones with firm contracts. The only difference between the orange and the green is that in one case, those customers, thank you very much. Yeah, so these two are the ones that but I shouldn't move. These two are the ones that I'm referring to. The only difference is that these customers may be, in some cases, they're connected directly to an interstate pipeline. In other cases, they receive gas through an LDC. So that's the only difference between the two colors. But other than that, they should have the same level of priority. And lastly, there are these two, the two boxes here represent the customers that have interruptible contracts, and those have the least priority. So that's the existing situation In the AEA model, which is the model that implements our proposed initiative that combines the NASB and the RTO position paper initiative, what you can see is that there is one additional box here, the one in yellow, and that refers to those power plants that enter into these AEAs, right? They get kind of higher priority and they get served, they receive their gas right after the LDCs. And so they would kind of out-prioritize other firm customers, and obviously they would also go before the interruptible customers. So our test system is this one that I'm presenting here, a test system that covers 8 states in the northeastern United States. These states are part of 4 gas pricing zones that you can see here. The ones that you may be familiar, you may have heard of, are this one, which is Transco Zone 6, and then this one right here, which is the New England region. That's the Algonquin kind of hub region. These are incredibly constrained regions, while on the other hand, these are less constrained, and they're also the green, for example, the green region, which is Leidy, is where a lot of the natural gas production in Pennsylvania is taking place. So those are generally less congested, and they have more production and lower prices. The period that we're looking at is the 2014 polar vortex. And obviously the polar vortex it lasted for a few days, but we are looking at a period of 25 days because we want to have a little bit of, obviously, a few days before and some days after of kind of normal operations. And so overall, we have a total of 25 days, that period that encompasses the polar vortex. It incorporates the polar vortex. Oh, this is another thing I wanted to show you, which is where the power plants that are critical to enhancing grid reliability are in our network. These are the power plants located in these counties where the red dot is. Those are the power plants that need to get additional gas so that they're able to reduce the unserved electricity demand in the network. And those power plants would be the ones that enter the AEAs. They enter the bilateral contract. If I have a power plant, say, sitting here, I don't need that to have a bilateral contract because it's not going to help with reducing unserved electric energy if needed. So we present 2 sets of results in the paper, and I'm just going to, in the interest of time, I'm just going to focus on the second set of results, and I'm going to show you just a couple of highlights. In the second set of results, we are kind of considering contracts that are established between power plants and industrial customers that are in close proximity. And by close proximity, I mean that they're literally sitting at the same gas junction, or they're sitting at adjacent gas junctions, and there is available pipeline capacity between the 2 junctions. And this is kind of a more realistic scenario, if you wish, relative to the one that we considered in 1, which was supposed to be an upper bound to the amount that could be potentially reallocated. But again, in a situation of emergency, you could probably have these contracts, this reallocation could only happen at the same location or in close proximity. The other thing that we did in this case is we assumed, and I think this one is too strong of an assumption, we might need to relax it. We assumed that only industrial customers that have dual fuel capability would enter into these AEAs. The idea being that If an industrial customer has another way of, like, say, maintaining their production process using an alternate fuel, they might be more willing and able to enter into the contract. Again, in reality, I'm no longer sure that that's really the case, because assuming that you pay that customer, that industrial customer, enough, if you pay them their value of lost load, they might be willing to switch off even if they don't have any dual fuel capability. So that might be a little bit too strong of an assumption. And that's the reason why we're currently working on a third set of results in which we only look at close proximity, but we'll disregard the assumption of dual fuel capability. So do I have time to, okay, yeah. At the end, yeah, let me just kind of maybe show you one thing, which are the net benefits here. The days that you see here plotted on the x-axis are the days in which there is unserved energy during this 25-day period. And these are the days in which the contracts would be triggered, right? Because that's when the reallocation would happen. Like I was saying, the net benefits would have two components. There's going to be a reduction in system costs because there's less unserved energy. But on the other hand, there's going to be a compensation to the industrial customers of their value of lost load. The difference between these two is going to be the net benefit for that particular day. So what's the magnitude of the net benefits, which was the question I asked at the beginning? At the height of the crisis, which is on January 7th, the net benefits of this proposed initiative are about 12% of the baseline system costs, which are the costs of operating of serving electricity demand in the baseline model. The baseline, we didn't have any contracts implemented. If you look at the other days, so if you exclude January 7 and you just take an average of the net benefits in the other days, you're roughly between 7 and 8% of the costs in the baseline. So the conclusion, so now we've kind of quantified the impact of this proposed initiative, and the conclusion is that this proposed initiative could help, but it's only, obviously, it's not solving even most of the problem, right? It's solving only 10% of the problem, and the problem would be unserved electric energy during these instances. Obviously, there's going to be a need for additional and stronger, broader regulatory reforms. And we need to also understand if the constraint is on the number of firm contracts that are signed on the power plant side, or maybe there's just too few contracts on the industrial side at the locations that truly matter. So that is something that, again, it's a spatial analysis of results that we are doing right now. And with that, maybe I will just pause and leave some time, like 15 minutes for Q&A. These are some of the things that we're thinking about, some of the additional directions we're thinking about, but I'd be happy to take your comments and questions. I mean, here? No.
Okay, we'll start with some questions in the room first.
Okay, thank you again. And yeah, please, I welcome questions. Is it one gentleman over there, please?
Maybe my question is a little bit out of the purview of your talk, but natural gas is a fossil fuel.
Mhm.
And that's contributing to climate change along with other fossil fuels. So what are your thoughts about moving away from all the fossil fuels as quickly as possible? And I might also add that these winter storms, as I understand it from Australia, are related to polar vortexes, and that's another sort of part of the erratic weather patterns created by climate change. So that's a very broad question, so it doesn't get into the specifics of your talk. But, you know, Trump is now back in office, and his view is drill, baby, drill.
Excuse me, just let's take it to a kind of technical question. I think it's going now. Thank you, please.
I think, so thank you for the question. I think it's definitely important to move towards renewable generation capacity, but we will need, I think, unless we have breakthroughs in terms of energy storage, we will continue to need natural gas to firm our like generation mix, right? And so that's the reason why I think that thinking about interactions between how the gas market and gas systems work in general and electricity systems is still important and it's still relevant. We need to think about this because we need to understand how the two components, the two systems operate together to be able to support the green energy transition and firm that renewable power that you're talking about.
Thank you. Thanks.
Thank you for the talk, Professor. I had a question about who pays in the end for the benefits that you measure, right? Because obviously customers benefit from having uninterrupted electricity supply, but I imagine for gas generators, they're paying a premium and they need to cover that cost. So did you look into what kinds of revenues they could make if they generated during those peaks using the AEAs that you studied, or any other way that they could recover those costs of contracts?
This is a very good question, and the short answer is we haven't looked at that yet, but it is a real problem, right? Because if you think about the situation right now, the power plants are, like I mentioned at the beginning, the power plants are not even able to recover the costs of the reservation charges. They're not able to pass that through the customers. So if they had to pay to kind of get access to the gas, an obvious question is, okay, so how would they recover their costs, right? If they're not able to bid them in the market, and so I think that we've always thought about that as like almost like a next step in the analysis, because once we see that there is a benefit, then the obvious next question would be, okay, how do you enable the power plants to enter into this mechanism and to recover their costs? So I think that's a very fair question and a very relevant question to ask, but we haven't thought about that yet. Yeah.
Maybe we can take a question from the online audience. For the option of auctioning the unused gas, has it actually been done in industry, and how can we implement this? And eventually, do you need to extend the infrastructure, or will just stay with the current infrastructure?
With the current. So if I understand, just to make sure I
There
understand.
are multiple questions. Yeah, the first one would be effectively for the auction of the unused gas capacity. Has already been implemented in some way?
The auction for, okay, so so yes, the auction for unused gas capacity is implemented here in Australia. So if there is any unused capacity any day, then that capacity gets auctioned and it can be procured through an auction. Now, this is a mechanism that works during regular days to reallocate capacity. But to my understanding, it has not worked during situations like during critical periods. And that's because during critical periods, there's very little unused capacity to begin with. And so, again, it hasn't been used in Australia for the purpose that we're considering. In the United States, there is something that is not exactly the same, but it's called the capacity release market, which it doesn't work as an auction, but it was designed for buyers and sellers to share the excess capacity. And what we see in the US is that the capacity release market does not work during these critical periods. In other words, there's no release of capacity during these critical periods, which is the reason it makes me wonder whether the auction mechanism for unused capacity could be truly effective during
When
like
there's
when there's no capacity. Yeah. So
and maybe, you know, just to kind of the second part of the question, maybe there would be a point where you might have to extend the infrastructure to build
for
new
sure.
infrastructure.
Yeah.
Right.
And yeah, absolutely.
I mean, a question again linked to this for me. There may be points, for example, remember years ago in Great Britain under similar conditions, people were starting thinking, what do I disconnect? Do I need to disconnect effectively some electricity customers because I do not have enough gas to support the gas power plants, or can actually disconnect customers for gas customers for different purposes. It can be industry, it can also be eventually heating, and so on. So at what point do we need to perform this kind of consideration in terms of disconnecting gas customers, maybe even residential customers on the gas side, like for heating purposes, for example? Because at some point, like there will be still, some critical needs for electricity, for heat. So who do you disconnect? Have you considered this, or hopefully we stay away from the question?
We have stayed away from that because we are like it is our understanding that like the pipeline operators, at least in the US, I don't know, in other parts of the world it may be different, but the residential and commercial customers for space heatings, they are untouchable. They're untouchable. They're considered essential human needs. And so it would not be possible to curtail those, which is the reason why even in our model, we don't even like try to curtail those. Now, I think where the problem lies is that if we move towards a future where there's going to be more and more electrification, including electrification of heating, what's going to happen is that maybe the electric power sector is going to start serving those essential human needs. It's not just about the LDCs serving the essential human needs for space heating. There's going to be more electric power plants that serve those essential human needs. And so that's the reason why I say I think it's important to think about these problems, because otherwise, if we don't even have a way to consider allocating gas or thinking about ways to allocate gas, we just keep doing what we've been doing for 50 years, which is kind of what they're doing right now. But that seems to be potentially very problematic in the future that we're going to have in the next 10, 20 years.
Let me push a little bit on this one.
Yes.
Effectively, it's like if you end up disconnecting gas plants, and you will have to disconnect like customers, like residential customers on the electricity side, possibly could be even worse, right? So you do not disconnect some gas customers and residential heating, but you have to disconnect residential customers for electricity and leave them in the dark. So that can actually be even worse. So you're still disconnected. You need to make a decision. Do I disconnect gas for heating, or do I disconnect gas for electricity?
For electricity.
And when they both involve residential customers, there's going to be like a tough one.
Yeah.
The other point is, I think we've seen this in Texas, that you may think of not disconnecting the residential customers for heating, but then eventually you disconnect electricity, and therefore the gas system will not work anyway. So the heating systems for residential customers will not work anyway without electricity.
Absolutely. That's
And
absolutely.
again, so like physically, somehow we see a coupling, then the markets will not see. So from the market perspective, oh, the residential customers for heating, they are untouchable. Fine, it doesn't help, because the moment that you disconnect electricity, because of the same reason physically, then you
The
have to
furnace doesn't
disconnect.
work. Yeah, no, that's very true. That's very
So
true.
yeah, I'm saying I'm pushing here, but it's really like for me, the need to integrate more the physics and the economics of the systems, because clearly the way that electricity and gas markets work do not clearly account for this physical
These
interaction between two
interactions.
infrastructures.
Absolutely, that's true.
All right, okay. You were probably more a comment than a question anyway. Are there other questions here? All right, okay. Then let me, please join me again, thanking Chiara.
Thank
Thanks so
you.
much. You were very good. And yeah, happy to hear that things have been done here in Australia. Maybe can bring something back to
Yeah.
US actually in terms of auctions for
Yeah,
unused
no,
capacity and so on.
I've been having some good conversations with people here who've been explaining and telling me about the centralized auction here. Although my question was always, okay, do you use it during emergencies? And they're like,
There's
no, we don't.
capacity. Yes.
That's just on a regular basis.
Yeah.
And so, that's when they
No,
have
but
unused capacity.
That's definitely very interesting point.
Yes,
Thank
it
you.
is very interesting. Yeah.
Thanks again.
Thank you very
And
much.
thank you everyone.